Hey everybody, it's Mr. Carr again. Today we're going to be looking at section 1.7, talking about inverse relations and functions. Okay, so part of what we're doing today is we're going to be focusing on the graphs of functions to determine whether or not they have inverse functions, and also finding our inverse functions algebraically. Okay, and also looking at it graphically as well. So first thing we want to talk about is a new thing called a horizontal line test. A horizontal line test tells us if a function f has an inverse function f to the negative 1. That's our inverse notation. If and only if each horizontal line intersects the graph at most 1 point. So it's kind of like the vertical line test, but instead of testing for just a function, we're testing to see if if an inverse exists for the function. Okay, so when we look at this graph here, we can see that the blue line, we have multiple lines here, but if I start like this, here's my horizontal line, and I drag it through it, and technically is only hitting the blue graph at 1 point at a time. So this passes this horizontal line test. Okay, so if a graph of a function f has an inverse, it's said to be 1-to-1. Okay, so a 1-to-1 function is one that does have a inverse function tied to it. Okay, so remember, just to be a function, it has to pass the vertical line test. To be a 1-to-1 function, it has to pass the horizontal line test. Okay, so any function has to have one input value goes to only exactly one output value, but a 1-to-1 function is every output value has exactly one input value. Okay, so how does this look on here? So here's a graph of f of x equals 4x squared plus 4x plus 1. We get a parabola with our quadratic, with our quadratic function here. With that parabola, you see here's just one line of many, but it crosses twice, right? It crosses here and here. So when you graph it and you check with the horizontal line test, if it hits more than once, there is no inverse function in this case. Okay, so because it fails the inverse line test, this does not exist. There is no inverse here. Okay, so this graph is good because it leads us into, before I get into the actual finding of it in this case here algebraically, let's quickly talk about what does it mean by an inverse then. So I'll bring up our Desmos here. If I give you a function like this one, here's y equals 3x plus 2. The dashed line is y equals x. An inverse function is one that exists where it takes it and flips it. So here's actually the inverse function here. You can see that right at this intersection point, the blue and green graphs are shared and they're on the y equals x line. Green looks like it's flipping over y equals x, so it's a reflection over that line. This is what we mean by a inverse function. So again, it has to pass the horizontal line test in order to just exist as an inverse. Okay. The other thing about this I want to point out is that every point that's on the graph is the same distance to the y equals x line as it is to the other line. So for example, I mean, I can go on a distance on an actual angle, but if I look at this point here, roughly, it's 2 spaces away to get to that line. And that's 2 spaces away to get to that line. So I can go 2 up, I can go 2 sideways. They meet at the same line. It works for every point. So this one right here is at negative 2/3 and 0. And then this point right here is right there at 0 and negative 2/3. So it's the same distance to the y equals x line. Okay. So that's what I mean when I'm describing inverse functions and what their graphs look like if they're flipping over the y equals x line. To find an inverse function, first of all, we want to determine does an inverse exist? And we do that with the 1-to-1 check with the horizontal line test. In the equation, you're going to take f of x and replace it with y and also swap the x and y. Okay, so we're going to swap x and y here. Once you do that, you're now going to solve for the new y. And once you're done, you're going to replace it with this notation. Remember, this is f to the negative 1 like that. That is our inverse notation. One more thing to set up on here is when we find our inverse functions, there are times that we're going to create restrictions on the domain. Any restriction on the domain of the inverse function is actually because of the range of our inverse. So here what we're saying is the domain of my given function is going to end up being the range of my inverse function. The range of my first function is the domain of the inverse function. Sounds a little bit weird, but we're going to take a look at that and see what it looks like both graphically and algebraically on this next example here. So find the inverse function algebraically. Okay, so step 1, let's make sure an inverse exists. I can go to my graph. I can go to my graph if I want, use your Desmos or graphing calculator. I know roughly speaking, the graph is going to look like this because it's a square root radical. It's got a vertical stretch and is moving one to the right. So it's going to look something like this. Okay, so if I double check my horizontal line test, it's going to pass. Every output had only one input to get that went to it. So it does exist as an inverse. So since it does, we're going to go ahead and do the swap on that. So instead of f of x, I'm going to change it to a y. But then what I'm really going to do is I'm going to make that x now is equal to 2 times y minus 1. Okay, so remember, this is what I did here. I did y equals 2 times the square root of x minus 1, and then I swap out the x and y's. The goal now is to solve for y. So when I do that, I'm going to undo the order of operations here. So I have subtraction, I got square root, and I got the multiply by 2. So I'm going to start with dividing both sides by 2. So that'll be 1/2 x is equal to the square root of y minus 1. From there, we're going to square both sides so we can get rid of the square root symbol. So I do that, I got 1/2 times 1/2 is 1/4, and that'll be 1/4 x squared. And that's going to equal to y minus 1. And my final step here is to add 1 to both sides. So I have 1/4 x squared is equal to, 1/4 x squared plus 1 is equal to y. Now, my final part of this is to state this as an inverse function. So instead of writing as y, I'm going to write f to the negative 1 of x equals 1/4 x squared plus 1. Now, the restrictions on the domain. The key to remember about this is the fact that my original function, let's look into both domain and range of that. We know that this is a positive 1 in the x direction, so my domain is going to go from 1 to infinity. That's my restriction on the original function. The range is going from 0 to infinity. Okay, so what that means is for my new function, the new restricted domain is actually going to be right here. It's the same as that one. So it's 0 to infinity. Okay, so let's take a look at what that looks like. So I'll go to Desmos right here. Here's my original function right here. There's my, let me change that. Yeah, no, we're good. So there's my original radical function. And then here is my inverse function. You see that how it crosses at that, like that point that is sharing on the y equals x line, it's flipping over. Now notice I already put this restriction on that x has to be greater than or equal to 0. If I take that off, I get a quadratic, but this whole thing is not the inverse of my radical function. It has to be this restricted version here. So when I do this, okay, by restricting that domain, okay, this is a part of it, but the rest of that quadratic does not exist according to what's in inverse to this function. Okay, so we're doing that domain restriction to make sure we have something that is fully an inverse of the original function there. Okay, all right, let's do one more example, I believe. Okay, so determine whether g has an inverse function for g of x equals x over x minus 2. If it does, find the inverse and stating restrictions. I'm going to just go ahead and go to Desmos this time. This is my rational function right there. If I zoom out a little bit, you can see that it does have inverse. It is 1-to-1 as I go through all my horizontal lines there. Okay, so I'll come back here. We know that it has that, so I'm going to say y equals x over x minus 2. Swap the x and y's, so we have x equals y over y minus 2. Okay, so from here, it's about solving for y. It gets a little tricky, but the algebra is not too bad. If I multiply both sides by y minus 2, okay, so I'll just do that right here. I'm going to go ahead and distribute the x now. So we get xy minus 2x is equal to y, because this will cancel out there. Here I have two y variables. In order to be able to solve for y, I need to get them together. So I'm going to subtract y to this side, but also add 2x to the other side. We want to get xy minus y here is equal to 2x. From here, we have y as a common factor. So I can factor that out of this left expression here. So y is going to be multiplied by x minus 1, and that equals 2x. And then I'm ready for my final solving step, where I divide both sides by x minus 1. Okay, so when I come here, I'll have y is equal to 2x over x minus 1. But then for my inverse function idea, I'm going to rewrite it like this. So that's my inverse function. Now, I got to look for any kind of restrictions on this domain. if you remember from before, we have a rational function where we have the degrees are the same in my numerator and denominator. So because of that, it is going to be the ratio of the leading coefficients for my horizontal asymptote. Now, the horizontal asymptote is important. So if I have a vertical asymptote, is going to be at x equals 2 because I cannot have a positive 2 for my x value. Horizontal asymptote is the ratio y equals 1 over 1, which is equal to just 1. That horizontal asymptote is important because when I go back to my graph, you can see I just graph y equals 1. The graph is going to approach it from both the kind of top and bottom, but it's never going to cross that. So if I look at my domains and my ranges for this first one, oops, that means my domain of the original function is going to be everything except 0, or sorry, everything except 2. So I can say it's negative infinity to 2, union 2 to infinity. For my range, it's negative infinity to 1, union 1 to infinity. Okay, so those are my domain and range for the original function. Since we're looking at this range is the original function, that is also going to be my domain for the new function, the inverse function. So this domain with its restriction is going to be negative infinity to 1, union 1 to infinity, which makes sense when you can look at this right here. Well, our new denominator is x minus 1. That means that 1 is the one value it cannot be. Just for one final thing, take a look at the graph of those. So here's the 2x minus 1. It's a little bit tricky to see, I feel like. Oh, come here. But it is each of those two curves are kind of flipping over. You can also see that if I type in x equals 1 here, that is the new, here, this one, that is the new vertical asymptote for that one, and that's the one value that my function cannot be. Okay, and that's it for today. So we're going to talk more about some other parts of our confirming whether or not we have inverses for the next lesson. But today we're just making sure we understand what is an inverse function, how it reflects over the y equals x, and how to find that inverse function if we're given a function. Okay, and that's it for today. Take care, everybody.